Okay, finishing up again really fast because I got cut off again. So, we saw the rules. You don't really use addition and subtraction very much in physics, so much more common you'll see multiplication like 5.4 times 10.3. I mean, I should probably give you an example that involves the sig rule, so 10.0. And let's say for no reason we'll add in 1/2. So solve this problem using the sig fig rules we discussed. Use the same rules for multiplication, division, powers, logs, sine, cosine, lots of stuff like that. Good job, you did it. If you just multiply it out, you'll get 5.4 times 10.0 divided by 2 for 27. How many sig figs? Not that many. 3 sig figs, 2 sig figs, 1 sig fig. So our answer should have 3 sig figs. 30 is the closest. Tens place only number to 27. You round up to 30. Should we do a decimal place? No, that is 2 sig figs, we only need 1. But here's the example I wanted to go over last time. What if this were not just math? What if we were doing a real formula? Like the area of a triangle, you guys all know, it's 1/2 base times height. Or 1/2 base times height over 2, same thing. Well, let's say 5.4 meters is the base of the triangle, and 10.0 meters is the height of the triangle. Well, same thing, 1/2 base times height, 27 meters squared. Should we do the same thing? Should we round to 1 sig fig because this 1/2 in the formula has 1 sig fig? What do you think? We should not. You have to think, don't think about the rule, think about why the rule exists. Sig figs exists to tell us how precise a measurement is, whether it's exact or not exact, whether there's some uncertainty. Is there any uncertainty? Do you guys think your trig or geo teacher was like, I think the formula is 1/2 base times height, but it might be like 1.07 over 2.3 base times height? No, it's definitely 1/2 base times height. This is a certain value. Several numbers are certain. You don't write all the sig figs, but they're there in your mind. Numbers like e and pi also have like a trillion billion sig figs if you wanted to get way into that, like maybe also like square root 3. You don't see the sig figs, but there's no uncertainty. So when you do this multiplication, pretend it has basically infinite sig figs, even though you can't see them. It doesn't have infinite sig figs, but really, there's no uncertainty. It's an exact number. If the formula for 1/2 base was actually like area equals 1.000000000 over 2.000000000 base times height, that would be a little more clear, but we don't write that because that kind of seems silly. Just there is no uncertainty in 1/2 base times height. You'll see a lot of this in physics. You'll see a lot of formulas like d equals 1/2 a t squared. Don't worry about what it means for now. The 1/2 is certain. If it's printed in the reference table or the grading sheet, it's a certain value, so 1/2 at squared. No uncertainty. The number of sig figs in D will be the lesser of the number of sig figs in A, and the number of sig figs in T. The number of sig figs in this 1/2 doesn't matter because it doesn't really have sig figs because it's not uncertain. So that's a good rule. And now, of course, the big question you guys all care about, will we have to do sig figs on projects and tests and homework and quizzes and stuff? No. Okay. One last thing so we can move on to our next thing. This also doesn't really relate to the class super much, but it's good to know. So let's say you're a real researcher and you're getting real data and you measure like a lot of things. Let's say you measure, I don't know, the height of tree samples or something. You'll get all sorts of values like, oh, this one's 17, this one's 20, pretty. This one's 45. Great. If you're a real researcher, you're going to get a lot of data, and it's going to be all basically just random values. A lot of them will end in 5. If you think about it, about 1 in 10 will end in 5 because there's 10 digits, 0 through 9. A lot of them end in 5. So if you collect a lot of data, you'll get a lot of values, and just because of the law of large numbers, a lot of them will end in 5. You'll have some 15, 25s, 35, 45, 55, 65. Obviously, yeah, all of them. Okay. You guys all know the rules of rounding. If you have to round this to the tens place, it would round up to 20. If you round this to the tens place, it will round down to 20. And most people think the rule, when you have a 5, you round up also. That is fine. You probably learned it like elementary school, and it probably worked for you for most of your life. That's good. But think about this. If you round 0, 1, 2, 3, 4 down, and you round 6, 7, 8, 9 up. Oh, okay, no, sorry, you don't round 0. If it's a 0, you don't have to round, sorry, you round it. If you round 4 digits up and 4 down, or I switch my hands, if 4 up and 4 down, that's fine. But if you always round 5s up, and you're a big researcher and you get a lot of data, like your whole job, your whole day is just making measurements and recording and rounding and doing calculations, if you round every single 5 up, and that's 10% of all your data, and you always round up, you actually make your data half of 10%, about 5%, not quite, but you make about 10% of your data a little bit higher, a tiny bit higher than it would be otherwise. It depends on the measurement exactly. I know this is a very contrived example, but it should make sense to you. If you always round 5s up, you're always getting your data a little tiny bit higher than it actually is if you didn't round. So in physics labs and science labs, there is actually a way to round that's not just always round 5s up. You always round 5s to the nearest even number. Obviously 5s are not even, so that doesn't make any sense. If I have 15 and I want to round to the nearest 10th, I'll round up to 20 as normal. But if I have a 25, look at the digit in front of the 5, not the 5, the next digit, the 2. If it's odd, you round up. If it's even, you round down. So 35, the 3 is odd, you round up. 45, the 4 is even, you round down. And this is a real rule that people don't really talk about very much, but it does make sense, because if you were getting like 1,000 data points for your tree samples, you don't want to accidentally overestimate the height because of your rounding. So technically, when you guys are in lab doing measurements, you should technically, if you have to round 5s up if the number before the 5 is odd, and down if the number before the 5 is even. That splits the 5s, so there's no bias because of the rounding. That's very good. So that's great. Good job, me. I did it. I'm a great physics student. Won't really come up. You don't really need to round very much in lab. Mostly you estimate with sig figs. We'll practice that in class, and that'll be good. There's one last thing called accuracy versus precision. And then we're done, I promise. We finally finished this lesson. Accuracy, precision. Okay. Most of the time, in real life, layman's terms, they mean the same thing. But that's not the case in physics all the time. Measurements can be accurate and precise, or only one, or neither. They're accurate if they are not wrong, if they tell you information that's not incorrect. They're precise if they tell you information that's very exact, that tells you a very specific amount of information that goes to a large number of sig figs, basically. So here's my amazing meter stick. It's 1 meter. It says it right there. If I measure the height of my Lamb magnet, it is accurate that it's above 1 meter and less than 2 meters. So that's accurate, but it's not very precise. If I want to be precise, I'll use decimeters or centimeters or millimeters. In case you guys didn't know, these tiny little lines are millimeters in most meter sticks. That's much more precise. Precise is going down to the smallest thing. Accuracy is whether or not your measurement is right. This is a pretty big meter stick. Just kidding, they're all the same size. But this meter stick is kind of big and clunky. What would happen if I just took the ends right here and I just chopped off the first 10 centimeters? I just chopped it, gone. And then I used the meter stick to measure things. But instead of putting this part on the ground, it's gone. So now I put the ground goes like right here. Bad example. Let's say I'm measuring this clock. I want to measure the width of the clock, and I gotta make a measurement. But let's say my meter stick kind of broke, so now my measurement starts here. This is still really precise because I'm still going to the nearest millimeter. But now, if I measure like this, my measurement's not going to be accurate. To measure accurately, you gotta measure from the edge right here. That should make sense. So things can be accurate, but not precise. Another common example people talk about, imagine you're shooting like a crossbow at a target. And you have like 10 crossbow bolts or whatever. And you shoot them all, bam, 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 and they all hit the target. Well, you didn't miss the target. You got them all. That's good. That's pretty accurate. That's good. But if your shots are all over the target, that's not very precise. Let's say you have a really fancy crossbow with like a really powerful scope, and you aim really well. You're a master crossbow person, and you shoot, and you go, bam, 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 bam. All your shots are perfect, but for some reason they all miss the center. These are not very precise. They're all off. In fact, let's say they were still precise, but they were so off. They all hit off the target right there. This is actually pretty common. When people like get competitive in archery or shooting or something like that, they might have like a thing that I can definitely show you guys because I have totally already set it up. They definitely have a, no, not that. They might have like a scope. A scope is like a little telescope that helps you aim your crossbow. It's right there. Oh, why am I going crazy? I'll edit this out in post-production, so it'll be fine. Don't worry. It's fine. Okay. There's these little dials. What these dials do, depending on wind and air and other factors that like are just built into your hypothetical crossbow, you need to adjust the sights. If you don't adjust them properly, you're going to end up with what we saw here. All your shots will be really good. If you're a great shooter, they're all going to be super close together. They're going to be very precise. They're very exact, but they won't be very accurate. So that's my example. Another example, hopefully no one can hear me right now because this is a great example. You know, like there's lots of like dating sites in the world. There's like Tinder and like Bumble and like Hinge and all. I'm on like all of them, every single one. Don't go check. Just trust me. I'm on every single one. And I only date people who use metric system because Americans are like the worst. It's not like a race thing. Like Europeans are fine, Africans are fine, Asians are fine, South America, anywhere besides US, I'm all about that. So a lot of people also. So okay, that's my story so far. Everyone okay? Following along? Good. A lot of people list their height on these dating sites because they're kind of like they have no personality, so they use their height instead. So I do that too. I could say I'm 2 meters tall, or I could say I'm 2.0 meters tall, or I could say I'm 1.8 meters tall, which is my real height, about. Close enough. 2 meters is less precise than 2.0 and 1.8. But if I said I was 2.0 meters tall, and then this person agreed to meet with me, and then they met me and I was not quite exactly 2.0, more like 1.8, that would be kind of disappointing for them. This 2.0 is not accurate, but it is precise. It goes down to the tenth. So it's not accurate, but it is precise. If I said my height was 1.8 meters tall, then that would be accurate and precise. So that would be the best measurement. But if I want to be super sneaky, I'll just say, oh, I'm 2 meters tall, because this only has one sig fig. If I measure myself, I could say I'm 0 meters tall, 1 meter, 2 meters, or 3 meters. Well, none of them are right, but 2 meters is the best answer. Like a meter is, obviously, you can't tell because of the stupid camera thing. 2 meters, you guys should know because we learned about meters, is closest to my height. 0 meters, obviously I'm not 0 meters tall. 1 meter is pretty short. Most people are not really 1 meter, 3 meters tall. This 2 meters, it's not accurate. It's not precise. But it is accurate, at least compared to the other values. It is more accurate. So if you do a lot of rounding, then yeah, I am 2 meters tall. But it's not a very precise, descriptive answer. It doesn't really explain to this person how tall I really am. And they're probably going to be a little disappointed when they meet me in person. So that would be too bad. Okay, hopefully that helps you guys remember accuracy versus precision. They're not quite the same thing. Sometimes it shows up on certain tests, so it's on the curriculum. Hopefully, yeah. Okay, cool. See you guys in like 5 seconds for me, and like a day for you. Bye.